So there we go. All right, well, it's time to get started. Today's topic is propositional logic, and you might want to, just add an entry to your notes to mention today's date, which is the 22nd of September, that we are starting on this particular topic, because this makes it easier for you to kind of look up the recorded lectures, so you can actually, quickly locate, and rewatch if you need to portions of this lecture. I believe it is streaming. Um, it's supposed to be streaming. Let me double check on the other side. Yep, it's streaming. See, I have evidence that I'm streaming. Whether you can see it or not, that's a different story. But I can confirm that on this end, we are indeed streaming. Oh, screen sharing. Okay, that's the other thing. Right, right. Okay, that I haven't set up yet. I remember to do one thing and then forget the other one. All right, so let's see. Yep, there we go. Sorry about that. That's my bad. Forgot about that. All right, so now we get back here. I really need a bigger screen or a double, or a separate screen so I can track Discord traffic, without cluttering my existing screen. So, so there we go. I think my setup is still correct. So if someone can talk in the voice channel just to be, just so that I can test my audio setting, that would be great. Okay,
Test.
thank you. That's good. I got it. Good, okay, very good. All right, so now we are ready. Okay, now we are ready to get into propositional logic. So propositional logic, as I said a little bit earlier, has a few major pieces. So before I go into the nitty-gritty detail of propositional logic, or CNF, or proof by contradiction, that sort of stuff, let me just kind of give you a general diagram of the overall structure of this particular topic. It is a little bit complicated, so let me see if I can do a live stream from the tablet itself. Okay, so I'm gonna put this all the way over here, and oh, there we go. So let's accept it. There we go. All right, so I'm pretty sure you guys can see the screen right now. So what I'll do is I'm going to put in a few components that are quite important. Okay, so the major pieces. So the first major piece is propositional logic. Okay, this is one big piece. And I do have to kind of explain a little bit what it was originally intended for and how it has changed a little bit in terms of how we're going to use it in this class. So propositional logic is not new at all. Okay, Greek philosophers already started to get into propositional logic when they were exploring the logic, of arguments. So that's really ancient. So in the age of computers, okay, when we have computers, uh, propositional logic takes on a kind of different meaning. Okay, it takes on a different role because what we want to do is we want automated automated theorem proving. So we want computers to be able to prove theorems by themselves instead of having people to prove theorems. We have some success in this area, but it's not really quite sufficient to do what we want computers to be able to do. So I'll get into that in just a little bit. So propositional logic is kind of related to automated theorem proving because propositional logic is also a mechanism to prove something. Automated theorem proving is a little bit more difficult compared to propositional logic because the kind of proof that we need in terms of proving a program is correct does require quantification, and propositional logic does not deal with quantification. That would be predicate calculus or predicate logic, which we'll probably get into. I'm hoping we'll have enough time in this semester to also get into predicate logic. In terms of automated theorem proving, one thing that is kind of important is not to look at logical expressions or Boolean expressions the way we see it, and to use the kind of proof technique that we perform. So what is happening here is from propositional logic, we will start to talk about CNF. CNF as a term is already in the module, so if you have read ahead in the module a little bit, you will recognize CNF is conjunctive normal form. Conjunctive normal form is interesting because the premise is every single Boolean expression using all the operators that we are familiar with, such as conjunction, disjunction, negation, implication, equivalency, and so on. All of those can be translated into a very clean and neat format called CNF conjunctive normal form. So no matter how complicated it starts with, it can be a nested implication where inside on one side is an equivalence, on the other side is a disjunction, and then inside the disjunction you have a conjunction, and so on and so forth. It doesn't matter, okay? It doesn't matter how complicated the original expression is. It can still be translated into a very nice looking format, which is CNF. So now the question is, what is CNF going to do to help us in this case? There's a mechanism called resolution. So resolution is also related to propositional logic because it is what we call a production or an inference rule. So with the human kind of logic, we have a lot of inference rules. So, if you just look at propositional logic in any textbook or just on the internet, there are tons of rules. They're sort of equivalent to all the rules that you have in algebra, except in this case, those are for Boolean algebra. So lots of rules. As it turns out, if we convert everything into CNF, then we only need one particular inference rule, which we'll get to what an inference rule is. But we can consolidate everything to just resolution. Once we have CNF and resolution, because resolution is a mechanism that works on CNF, then we can also combine these two. Well, there's one more component here. This is proof by contradiction. Proof by contradiction. So at this point, you probably have heard about me talking about proof by contradiction quite a bit already. So finally, with this particular module, we'll actually get into what is proof by contradiction, how it works in general, and in this specific case, how we can utilize it to prove theorems in proposition logic, in a propositional logic system. So the focus that I'm putting into this particular module is not so much how we humans can make use of propositional logic, but rather how the computer can make use of propositional logic so that we can mechanically prove theorems. The idea is automation, okay? Because we don't want to do things ourselves, so we want to be able to automate. And the other aspect that is kind of interesting about this module is theorem proving can be considered as AI, as artificial intelligence, but it is very different from what people understand as artificial intelligence these days. Okay, because these days when people say AI, they're mostly talking about neural nets, machine learning and all that stuff. What we're talking about here, is not, probably cannot be easily done using neural nets because it's rule based, okay, it's very symbolic, and it is not, it doesn't lend itself to analog values, which neural nets are, they excel, at processing things that have numerical values. So that's kind of interesting because it is a different branch, a different kind of artificial intelligence. So that's the overall map of what we are going to do with this module. And as you can see, there are many, many components to this whole thing. So I just want to pause here and see if there are any questions, because if somebody has already read ahead of me, when they look at this big picture, they might have some questions already. All right. Oh, right. I forgot about relation. Let's finish relation first. I was too excited to get started with this new topic. But yes, we probably need to go back and finish relation first. So let's do that. All right, so with relation, now that you mentioned it, thank you so much. I remember that we are going to talk about antisymmetric relation. So let me look for relations, and here we have it. All right, so antisymmetric is the next uh, qualification or next property that we need to look into. A relation R over a set X is antisymmetric if and only if the following is true. So in this case, we only have two quantified variables. One is E and one is F. And the quantification is a universal quantification, which means, for every way to bind E and F to elements in X. Can they be the same? Absolutely. Can they be different? Absolutely. So what do we need to be true, knowing that E and F are elements of X? So this is the rule, okay? EF in R and FE in R implies E and F are the same. So that's the only rule. So this is an interesting one because it's not exactly the opposite of symmetric, and yet at the same time, it is also not the opposite. It's not. We'll see. Okay, let's go through some examples, because that way we will kind of we'll see what is and what is not antisymmetric. I am going to use mousepad. So this way I can just kind of use a text editor to put in some examples. So let's say X, which contains the set of the elements that we want to relate, is ABC. And R, which is a relation defined over X, needs to be a subset of the Cartesian product between XX. So the first thing we usually look at, based on what we have already discussed in the past, is the empty set. So the question is the empty set antisymmetric or not? So I'm going to let you guys think about this a little bit, and then I'll tell you guys what the answer is and why that is the case. So the question is the empty set is or is not antisymmetric? All right, so we got Jonathan saying it is. Okay, and anyone else? I mean, the key really has to do with the implication, and Jonathan already suggested that in his answer. All right, so I'm guessing no one else wants to give it a shot, because I guess we know the answer already. So the answer is it is antisymmetric. So let me go fix up my sentence here to make a conclusion. The empty set is indeed antisymmetric, because with an implication, we can see there's an implication here. An implication is true when the left-hand side or the precedent of the implication is false. So that means we have to look on this side here and see whether this conjunction is always false or not. Because if this conjunction is always false, then we are done, okay? Because we can now conclude that the implication is always true. So the conjunction has two parts. The first part is EF is an element of R, and the second one is FE is an element of R. So if R is an empty set, it has no elements. So that means no matter what you specify on the left-hand side of the is an element of operator, it's always false, because there's nothing, absolutely nothing in R. So that guarantees that both sides of the conjunction is false. and as a result, the conjunction itself has to be false. If the precedent of the implication is false, then the implication itself is false. I mean, it's true. Sorry, take it back. If the left-hand side of an implication is false, the implication itself is true. So this way, I can guarantee that R as an empty set is indeed antisymmetric. All right, let's take a look at another relation then. AA, BB, and CC. What about this one? Is it antisymmetric or not? Now we know this one is reflexive. Yep. We know it is symmetric. Yes. We know it is transitive. The question now is it also antisymmetric? In other words, given any two elements of X, okay, EF in R and FE in R implies E and F are the same. So on is correct. Okay, it is indeed antisymmetric. Because given these three are the elements, so the only time, so we don't have to worry when any component of the conjunction is false, because for those cases, the implication is going to be true. So the only cases where we have to start to think about is like, oh, what if the left-hand side of the implication is true? So the only time the left-hand side of the implication can be true in this case is when E and F are the same. So when E and F are both A's, then we have AA is in R and AA is in R, which is true. Does that imply A and A are the same? I would think so, right? Because A is just a particular value. It has to equal to itself. And then Jonathan says, can you give an example of R where it is antisymmetric but not reflexive? Oh, that's easy. That's easy. I'll get to that. And then BB is the same way. So if E and F are both B's, then we have BB in R being true. BB in R is true. True and true is true. But B equals to B is also true. So, not a problem. Okay, so let me go answer Jonathan's question. He wants something that is antisymmetric but not reflexive. Actually, we have that already. When R is an empty set, it is antisymmetric and yet it is not reflexive. I think what Jonathan meant was symmetric, not reflexive, because it's way too easy to find one example. Okay. I really could not read Jonathan's mind, but knowing the kind of question that Jonathan asks in class, the question of having something that is antisymmetric but not symmetric is a little bit more challenging. All right, so yes, absolutely. Yeah, it's really easy to do it. Okay, so all right. I do have to mention that we also have an example of something that is not symmetric. So we want something that is anti-symmetric but not symmetric. That's actually not hard to do. All I need is just AB, and we'll even stick in a BC in here. Okay, this is anti-symmetric. Why is it antisymmetric? Because if you want to find something that makes at least one of these two conjunctions true, we guarantee that the other side of the conjunction is false. Because if I make E equals to A and F equals to B, then we have EF in R being true, but FE in R is actually false because we don't have the other one. So when the conjunction itself is false, then we have the implication being true. So not a problem if I specify E being A and F being B. What if E is B and F is C? Same situation. So this is an example of something that is antisymmetric but not symmetric. Are we good so far? Any other special requests? Like, I want something that is antisymmetric, but blah, 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 blah. Because those are very good questions. If this really makes your mind work hard because you're trying to find some tricky cases, it's like, is it possible not to have this, or is it possible to have this, and so on. All right, so I'm not seeing any questions, and nobody seemed to be typing in the text channel. All right, let me give you an example where it is not antisymmetric. So we use R here, and this time we just make a very slight modification, and it is no longer antisymmetric. Because in this case, if E is A and F is B, then AB is in R is true, and BA is in R is also true. But A and B are not the same. So now we have the conjunction on the left-hand side of the implication being true, but then the equality on the right-hand side of the implication is false. True implies false is the only time an implication will give you a value of false. So there's that. Any other questions about antisymmetric? I'm not seeing any questions. Let's move on then. All right, so now that we have the four qualifications being reflexive, symmetric, transitive, and antisymmetric, now we can talk about partial ordering. So partial ordering is actually fairly easily defined, given what we already have, talked about. A set X is said to be partially ordered by a relation R if and only if the following is true. R is reflexive over X, and R is antisymmetric over X, and R is transitive over X. Symmetric is not important here. Okay, we're looking for the other three, but we don't need something to be symmetric. All right, so at least up to this point, are there any questions about what qualifies as partial ordering? When can we say a relation is partially ordering over a set? Are there any questions about that? No questions? Okay. So let's take a look. Oh, okay. Makes sense. Okay. All right. So what is partially ordering? So I'm gonna, this is the example that I give here is coming from a Australian beer commercial. So for those of you who want to find it, let me give you a link to it. So we want to look for beer commercial, rich, smooth. That should find it. There we go. Rich and smooth beer. Rich but not smooth. So all of these are references to the same beer, and it is I thought it was a Australian beer. I could be wrong. Skip. All right. So now that we have watched the beer commercial, it's okay. You guys can look for it and watch it yourself. Okay. So anyway, the idea is, what about someone? How do you? Okay. So in terms of okay, the relation I want to define here is at least as attractive as. Okay, now I am not trying to propagate social norm or anything like that. I'm just looking at this funny beer commercial and use it as an example for this class. Um, well, I can give you guys the link to it. Okay, let me look it up again, right? So, beer, commercial, rich, smooth, and this is the commercial. So I'm just gonna copy the link and paste it into the text area. There you go. So now you can look it up yourself. All right. Don't do it now, okay? Don't watch it now, because we are still in lecture right now. But after lecture, go ahead and watch that commercial. It's just kind of funny. All right. So now we have four types of people. So let me use the text editor to specify the four types of people. Okay. So first of all, so I'm going to call these category by we'll label these categories. So we have category A, which is rich and smooth. We have category B, which is rich but not smooth. And then we have category C, which is not rich but smooth. And then we have category D, which describes me being not rich and not smooth. There we go. Oops, can't even type smooth. There we go. So the idea is we want to define a relation, within this particular set. So you want to look at X as A, B, C, D. So we are only looking at these broad categories here. So the relation that we want to define, okay, R is defined as at least as attractive as. That is the relation. In other words, we want to find out whether A or B. Okay, so A or B means rich and smooth is at least as attractive as rich but not smooth. So does everybody understand what R is representing? Obviously, this is just a fictional kind of relation. I'm just using the beer commercial as an excuse so that we can look at something that is partially ordered. Are there any questions about what R is trying to define? The relation that we're trying to define is at least as attractive as. And we're going to use what the beer commercial is implying, which is rich and smooth is better than rich but not smooth. Rich and smooth is better than not rich but smooth. And then by implication in the commercial, we will also infer that not rich and not smooth is worse than the other three categories. Does that make sense? Okay, all right. So what we end up with is a relation R. And in this relation R, we will define AB. We will define AA. Now, why is AA in the set? Because I'm not trying to define more attractive than. I'm trying to define at least as attractive as. So a person who is rich and smooth is considered at least as attractive as another person who is also rich and smooth. That's why AA is in here. Okay, but certainly we get AB, we get AC, and we also get AD. In other words, the category of rich and smooth is at least as good as everybody else. Does that make sense? I mean, using the beer commercial logic. Okay, so this is beer logic. This is not a social norm that we should be promoting, but based on the beer commercial, this is the logic system. Then we're going to look at B. Okay, so BB, right? Because someone who is rich but not smooth is at least as attractive as someone who is also rich but not smooth. And then we have B, D for sure, right? Because D is the worst. Okay, there's no one who's going to be as bad as not rich and not smooth. Okay, that's where I am. All right, so now we can move on to C. Okay, we have CC. because for the same reason. And then we have CD as well. And that's it. That is the entire set that we are trying to define. So whether beer logic is smart or not depends on whether the person who's evaluating that logic also has had beer or not. For someone who has drunk enough beer, the beer logic may actually make sense. But for someone who's sober, we look at that logic and go like, I'm not so sure about that. AD is, oh yeah, AD is supposed to be in there. I forgot. I mistyped. So there we go. Thank you. So Matthew is correct. AD is supposed to be in there. We really cannot have two ACs because in a set we cannot have duplicate elements. So that's a good catch. Very good. Good catch. How about BC? Now that is a good question. BC is not in here because the beer commercial did not actually compare or implicate whether category B versus category C is better. Whether one is more attractive than the other one, it doesn't say anything about it. Whether they are considered the same, also not implied. Okay, it simply was not implied. How those two rank. So BC is not there, and CB is not there either because there's no information, and that is the whole point of this particular relation is partially ordered. All right. What about DD? Oh, very good. Okay, you got me again. DD is supposed to be here because you know people who are not rich and not smooth, they are ranked equally. Good job. Very good. All right. So, what is what does this have anything? What does beer commercial have anything to do with relations, right? With all those technical terms that we just mentioned, and what does it have to do with programming? So, as it turns out, it really is kind of important. Okay, so let's just say that we are trying to elect a person. Um, Beer drinker of the month. Okay, last time we had gamers and this time we have beer drinker. But before we proceed with this example, it's time to take roll. So I'm going to take a little moment here to take roll first. And let's see. Today's date is 2021-0922. And I thought that I had. Oh yeah, absolutely. It's right here. All right, so I'm going to edit. No, the word is not beer. I bet you some people are thinking, okay, tech is probably either using beer or the brand name of the beer. Nope, that is not the case. And it turns out to be just square. So square is the word for road taking today. I just put it into the text channel. And I'm going to save and publish. It should be, you guys should be able to do it now. I'm just going to double check to make sure the date and time is correct. Yep, September 22nd. And you have until 5:12 to do it. And you don't even have to know how to spell square because you can copy and paste. Alrighty. Okay, so Elijah said, and also the abbreviation of square. Yes, that works too. But I just thought, since I put the word in the text channel, most people would just, double click, Control C, click on the other side, Control V, and press the Enter key. All right, Tosh is typing. You got 100%. Congratulations. Good job. All right, so getting back to our example. Okay, getting back to the example. So if we are looking for someone, who is our beer drinker of the month, okay, And this particular month, it turns out that no one, okay, no one who is both rich and smooth, entered the contest. Everybody who entered the contest are coming from the other three categories. So now we have a problem because there's no actual comparison. There's no way to compare between someone who's rich but not smooth versus someone who's smooth but not rich. So we can no longer, sort the items in the array because this particular comparison operator is not totally ordered. It is only partially ordered. So that becomes a problem, okay? And that is the reason why we have to distinguish what is partially ordering or partial ordering versus what is totally ordered. So totally order, just add one more requirement. The requirement is R is comparable over X. What does that mean? Well, as usual, we're going to use a quantified statement to explain what that means. So this is the quantified statement. For all EF in X, which means, once again, E and F, they are variables bound to elements of X, ERF or FRE. In other words, this is really just short form of EF in R or FE in R. In other words, E and F, they have to relate in some way, okay? Either ERF, or FRE. Or both, okay? Both are fine too. It's just that we cannot have neither. And that's the only additional requirement in order to turn a partial order into a total order. So do we have any questions about partially ordered versus totally ordered? Okay. So the application of what we have just talked about here has to do with sorting. Okay, because anytime you want to have some kind of ranking, anytime you want to find the best, the most something, that sort of thing, you need to make sure that whatever comparison operator you're using, whatever method you have to compare, to relate items, is going to be totally ordered. Because otherwise, you cannot sort. Otherwise, you cannot find the most blah blah blah, or the best blah blah blah, or the largest blah blah blah, or the smallest blah blah blah. All right. So that is how this stuff relate to programming. And unless I see any additional questions, we're going to go back and resume our discussion of propositional logic. All right. I'm not seeing any text. So we're going to go back and resume our discussion of propositional logic. All right, very good. So with propositional logic, we'll first define something that is a little bit abstract. And this is the for tuple. If you want to find out how to type all of these kind of funny words, you just have to right click, show math as text command. And the first one is a math cal L, and then we have basically just uppercase A, and then we have uppercase omega, and then we have, this is supposed to be zeta, this is supposed to be alpha, and this is supposed to be iota. But using the uppercase English letter also works. So there we go. So that's how we enter all of these things. So what do they mean? I mean, what does A or alpha, what does omega represent? What does zeta represent? And what does iota represent? So this is a brief explanation. So A is, or alpha, is a set of symbols to be used. Symbols have no inherent meanings. So all we are doing here is to define what symbols can we use in this particular propositional logic system. Omega is defining what we call connectives. If you look up propositional logic, what omega is a set of what they call connectives. But which is really in the context of Boolean logic, they translate to Boolean operators. Now, you can also have subsets within omega. So within the subset omega I, where I is just a natural number, it determines the number of items connected by a particular connective. So omega 2 is going to be a set of connectives it would be the set of connectives that require two operands, two values. So conjunction would be in omega 2, disjunction is going to be in omega 2, implication would be in omega 2, and then is if and only if is also going to be in omega 2. Omega 1 would be the operators that only require one single value. So within the Boolean algebra that we are familiar with, there's only one operator like that, which is logical negation, or what we know as not in programming. So that would be omega. Zeta is the set of transformation rules, also known as productions, or also known as inference rules. Okay, so this is the what we contain in zeta is actually very important, because what it allows us to do is to convert, is to make new. Okay, I shouldn't say make, but it can look at existing well-formed formulae, which is explained, in just a little bit down here. So it's going to be able to look at the well-formed formulae that are known to be true, and then derive and label additional well-formed formulae also to be true. Okay, so I know that sounds really abstract at this point, but once we get to an example, we will basically be able to tell, oh, okay, so that's what it means. And then last, we have iota. So iota is a set of well-formed formulae that are just given to be true. So don't ask why these expressions are true. They are just given to you that they are true. So now we have one more thing that we need to define before we can actually use an example. What exactly is well-formed formula? So a well-formed formula is defined as follows. And I'm using the universally quantified statement. Okay, so everything in A is a well-formed formula by itself. So whatever element you put into alpha, by itself, each element is already a well-formed formula. And later on, I'll tell you exactly what kind of stuff we put into alpha. And the next thing is for every I in a 1 dot dot n, which is basically my shorthand of all the integers starting with 1 all the way up to n, and n is the largest number of operands for operators. So in the case of Boolean operators, we only have 1 to 2. Okay, so this set only has 1 and 2 in it. And then in here it says for each phi I, okay, if each phi I itself is a well-formed formula, and E is in omega n, then we know that when you apply E using phi 1, phi 2, phi 3 all the way up to phi n, that is also known as a well-formed formula. So this is where the definition the definition of well-formed formula is recursive. Okay, so the at the ground state, okay, the ground well-formed formulae will be simply elements from alpha. Okay, so that's where you start. And then using the connectives, which are basically just operators, you can form larger well-formed formulae. But each well-formed formula that you create can also be combined further with other larger well-formed formula using the connectives, and therefore we can construct larger and larger, bigger and bigger well-formed formula. So now is a good time to give you an example of what we mean by that. Okay. So we'll go ahead and say, A consists of false, true, P, Q, and R. Okay. So we are missing something that's really important, that we also need to put into the set of all the alpha, but it's okay for this particular example. And then we specify omega to contain, I'm just going to spell out the words, or if you prefer, we can use, this is just an example, so don't worry about the quote-unquote syntax. So we have the usual C operators, which is and, or, and not. And then the next one is zeta. We are not going to talk about zeta at this point. We also have iota. Okay, so I'm not even going to talk about iota because we don't need those. Okay, we don't need iota, and also we don't need zeta to understand what is a well-formed formula. So at this point, we know that um, is AWFF 0 is true. Okay, in other words, 0 is a well-formed formula. And I can also use English to write this out. Is a well-formed formula. P is a well-formed formula. Q is a well-formed formula, and then R is a well-formed formula. Why? Because all of these symbols appear in alpha, in the set alpha. All right, Jonathan is typing something. I'm gonna pause a little bit until he finishes typing. All right. I'm confused by the is a well-formed formula notation. Is it a statement suggesting whether A is a well-formed formula? That is correct. So it's a predicate. Basically, you can give the function, is a okay, one way to look at this is a well-formed formula is a function that returns a Boolean value. So you basically give it something, it evaluates, and it will come back and tell you whether that something is a well-formed formula or not. So that's what is a well-formed formula as a function is. It's also a predicate because anything that returns a Boolean can be seen as a predicate. All right, so the at the base level, everything in alpha are well-formed formula. So now we can start to use this and go like, oh, so if I join two well-formed formula using a symbol from omega, and I give it the right number of operands, the end result of that is also a well-formed formula. So that means you can make something like P and I said P and I type Q. So P and Q is a well-formed formula because P itself is well-formed, Q itself is well-formed, and the ampersand ampersand, the AND operator, requires two operands, which we are supplying. So now we can say P and Q is a well-formed formula. You can form some of the other ones. You can make complicated things like not R is a well-formed formula. Now, these are all just samples. Obviously, there are a lot more well-formed formulae. It's just that I'm giving you some examples of what is well-formed. What is not well-formed? I can give you something that is not well-formed. So if you only specify one side of an R, of an OR, like R OR, that is not a well-formed formula because you need something on the right-hand side of the OR too. Okay, so this is why not everything is well formed, but I think you got a general idea of what is well formed. So now we can combine these into even bigger ones. So P and Q or not R is also well formed, and so on and so forth. Does everybody understand now what is syntactically considered well formed? Are there any questions about the concept of what is considered well formed? Yeah, it's more like syntax. It's not; these are not even for logic. It's really syntax. It's structural. We are trying to determine, structurally what is considered grammatically correct. We're simply specifying syntax right now. There's no meaning whatsoever to these formulae because you can construct something that is stupid. Okay, so you can say, okay, 0 is in alpha, it is well formed. So that means 0 or 0 is well formed, which also means 0 or 0 or 0 or 0 is well formed, and so on. I mean, that's not useful at all, right? But nonetheless, all of these are structurally sound. They are grammatically correct, even though it's like you can just say false. Why do you waste all these or operators? Because I can. Okay, is that okay? All right, cool. So now I'm going to give you a question, okay? If I want to make a set of all the well-formed formulae, do you think that set is finite or do you think that set is infinite? So let me repeat the question. Okay, Jonathan answered that already. So the question was, okay, it's I can still repeat the question. So the question was, if I want to consider a set of all possible well-formed formulae, is that set finite, which means it only has a certain number of elements, or is it infinite, which means it can have there's no way to exhaustively list all the elements. The answer was it is infinite because I just gave you an example, right? Because if I just use this approach, take this one and then say, this thing or itself is also well formed, and then take that thing and then say that thing or itself is also well formed. I can keep doing this until the end of time in order to make more and more useless and senseless but well formed formula. Does that make sense? Does it make sense that this particular set is infinitely large? Okay, very good. So what I'm going to do next is to tell you guys what a proof is, okay? And I'll give you an example of what now iota becomes important. Okay, so in the discussion at this point, iota becomes important. So if I say, okay, in iota, I say, okay, true is true, not false is also true. But guess what? I got something that is kind of funky, and don't ask me why, but it is true. So I'm going to say P or Q is also known to be true. And I'm also going to say, okay, I'll just throw in some random stuff here. I'm going to throw in not P or R is also known to be true. That's iota. Okay, so iota is basically giving you the well-formed formulae that are known to be true. Don't ask, there's no derivation needed, there's no explanation needed why these particular expressions are here. They are just assumptions. Okay, they are known to be true. So iota really gives meaning to a propositional logic system because it is seeding the entire system with something that are based. These are the axioms basically, okay, and we want to see what we can derive from these axioms. So now is a good time to switch to the tablet because I want to give you a kind of graphical view of what we are talking about here and why I'm using the approach that I'm going to use to talk about why CNF is important later on and why resolution is also important later on. You're not seeing the live screen yet because it somehow times out and I have to stop sharing and then reshare in order for it to register again. So it should ask me, yep, right there. Click OK. Alright, so there we go. Alright, so what we have here is a infinitely large set, or I can use the term space. So let's just say that, okay, I'm going to use some fancy stuff here. I'm going to use a pencil, medium, okay. So I'm going to use this kind of as the boundary of the set of all well-formed formula. And somebody is already saying, but it's infinitely large. Well, that's why I'm not showing you the entire thing because it's infinitely large. So what's in here? Okay, so I'm going to show you what is in here. So what is in here are things that seem to make sense. Okay, remember this is known to be true, and it's also a well-formed formula. This is also known to be true, and it is a well-formed formula. We got P by itself, we got Q by itself, we got R by itself, we got not P by itself, and then we have P or Q. And then we also have not P, or I cannot remember now. Let me go back to my text box here. Not P or R. Okay. And then we have the stupid ones, right? So we have, false or false. And then we have false or false, or false or false. Okay, we got a whole bunch of not so really smart ones. And then we got false all by itself. We have not true all by itself, and so on. Now, obviously, I'm not going to give you an exhaustive list of the elements in this particular space because we have just established that this space is infinitely large. Okay, there's no way to list everything. All of these are well formed. Okay, you look at this thing here and go like, but we know this is false, right? Yes, we do, but I'm just asking, is it well formed? So this is the set of well formed formula. Okay, and what are we going to do with this? Well, what we're going to do now is we're going to label things that are known to be true. And then we will start to work with things that are inferred to be true. So you look at this whole thing here and go like, but how do we know what is true? We start with things that are in there that are elements of iota. So let me switch back to the text editor. Iota is defined in this specific way for this specific system. So true is known to be true, not false is known to be true. P or Q is known to be true, not P or R is also known to be true. And that's it, okay? So now we switch back to this diagram and then we start to label things. So we circle this and go like, aha, this is in iota, and this one is also in iota, this one is in iota, and this one is also in iota. Great. So what are we going to do next? So somewhere in here, okay, is a well-formed formula such as P and not R. For instance, okay, this is just an example. So the question is, can I prove that P and not R is also going to be true because we start with these four items? I'm waiting for the red dot to appear. Because we start with these four items known to be true, can we somehow label this thing to be true too? That's how we prove theorems. Okay, so what we see here is just a logical system. But when you think about your calculus class, when you think about your linear algebra class, and so for some of you, when you move on, especially if you want to graduate school, you might have to take abstract algebra and other things. But every single mathematical proof is really the same thing. Okay, you have some premises, okay, things that are just given to you to be true, okay, a whole bunch of stuff in this entire system where we really don't know whether those expressions are true or not. And then you have one thing here that you say, can I use what is known to be true to prove that this is true or not? That is the question, okay? That's basically theorem proving. How do we get there? Are we okay so far? Now, I can give you one thing that definitely has to be true. So, if I say P or Q and not P or R, don't you think this expression has to be true? Of course it has to be true, right? Because, all of these circled ones are true already. So if I know P or Q is true, and I know not P or R is also true, don't you think the conjunction between those two expressions that are already true has to be true? Of course it does. The question is, do we have a mechanism to connect to somehow let us label this thing also to be true? That is the job of the elements of zeta. The elements of zeta are known as inference rules, and what inference rules allow us to do is to say, hey, if you can find something like this, with a pattern to be true, then we can also derive, we can work on this and then generate a new pattern of another well-formed formula that is also known to be true. That is what each element of zeta is supposed to do. Do we have any questions at this point? It is kind of like an implication. So when we use the word implication, we are thinking about the meaning of these things. So instead of using the meaning of these things, I'm using this system here. Propositional logic is a mechanical system. In other words, it is no more than, it's kind of like your compiler, okay? The compiler doesn't really quite understand, what you mean when you say, oh, this is a loop, we need to do this, we need to do that. But it is very, very good at manipulating symbols and is very, very good at emitting object code after compiling your program. So that's what a propositional system is trying to do. It is simply a mechanical symbolic system to process things. It's a pattern recognition thing. I recognize this pattern on one side. I will now label something on the other side to also to be true. So it is not really based on the meaning of things. That's what we do, okay? What we do is we look at implication, we look at or, we look at and we associate those operators with very specific meanings. This system doesn't do that, okay? The propositional system does not really know what exactly is and, it doesn't know what exactly is or, and so on and so forth. It just has a symbolic processing system that will basically it mirrors what we can do when we prove theorems, but when the computer does theorem proving, it is all symbolic. It doesn't understand meanings whatsoever. Okay, so the next question is, well, Tech, can you give us an example of one of these propositional, of one of these, it's called an inference rule. Okay, so we'll go ahead and take a look at, certain inference rules. And I'll start with something that is really kind of strange. Okay, so an inference, well, not that yet. Okay, so but I do have to say, what is an inference rule? So it starts with this symbol here. It looks like a T that is rotated counterclockwise 90 degrees. Okay, on one side we specify a set. Okay, so this is called a set of patterns. And then on the other side, we have something here that is the resulting pattern. Now these are my description, okay? If you look up propositional logic, it has a definite term for what is on the left-hand side and a term for whatever is on the right-hand side. So I'm just giving you the really colloquial version of these terms. So on one side we have a set. This is a set of patterns. If all of these patterns are matched, okay, then we can use this mechanism to produce something on the other side and go like, hey, if I can find well-formed formulae to fit these patterns, then I can go ahead and generate a new pattern to as a well-formed formula and also say that those things are true. And then you look at this and go like, that is still pretty abstract. I have no idea what this means. So I'll give you a very simple example. So this is where we have to add certain things to alpha. So now we say alpha has all the things that we had before, that's just the dot dot dot. But this time we'll also include, I'm going to throw in 3 Greek symbols. So I'm going to throw in psi, I'm going to throw in phi, and also rho. Okay, phi is, oh, right, that's phi right there. Okay, so these are special, okay? P, Q, and R, okay, so the English letters, those are typically used to represent what we call variables. In other words, Each one can be true or false. We just have no idea whether it is actually true or actually false. Okay, it is just like a variable in programming. Okay, it can hold a value. They are of a Boolean type, and that's all we know about PQR. And if you need to have more variables, you can use STUV and so on. And then we have constants. Okay, 0, 1, these are constants. So they're typically just the way that we interpret 0 is false and then 1 is true, but they're constants. Okay, they're literal constants. Basically, they cannot have a different value. What they mean is cannot change. Whereas P, Q, and R are kind of like, we have no idea whether P is true or not because it is just a variable. So now we have the Greek symbols. So we have psi, we have phi, and then we also have rho. So these have also special meanings, or there's a special term to refer to these. And instead of using the technical term people use in propositional logic, I'm going to give you a term that actually best describe these things. I'm just going to call these things patterns. Okay, they're just patterns. Okay, so what do I mean by patterns? They're placeholders. Okay, the best way to say this, these are placeholders for well-formed formulae. All right. All right. So now we look at these things and go like, variables. I think we understand because we use variables a lot when we write programs. Constants, absolutely, right? Because in C and C++, especially C++, it has true as a constant, it has false as a constant, 0 is a constant, and so on and so forth. So we got constants, we got variables. What about these guys? Okay, they are placeholders for well-formed formulae. How do we use these things? So as it turns out, the Greek letters are only useful when you specify these transformation rules, okay, up here. So I'm going to give you one concrete example of a production or a inference rule. So the inference rule says, if you find a pattern psi and you find a pattern phi, okay, if you find those two things, then we can infer, okay, this symbol here means infer, then we can infer psi and psi and phi. That's one inference rule. Okay, so what does that mean? So what that means is you are the system, okay? You are the active agent in the system. You are basically going into the space of well-formed formulae, and you're just saying, can I find some well-formed formula that is true? Okay, if we can find one, we'll bind it to psi first, and then you ask, can we find a well-formed formula that is known to be true at this point, and then you can bind that one to phi. Once you satisfy this requirement, then you can say, oh, you know what? I can now say that this well-formed formula is also true. So let's go ahead and apply this particular transformation rule in the diagram that we have seen already. So the way I'm going to do this is I am going to copy and paste this particular inference rule, go back to here, paste it so that we can actually see the inference rule, and then we say, okay, how do we apply this inference rule? Oh, let's just find something that is known to be true. Now remember, the initial things that are known to be true, they all come from iota. And iota is a finite set, typically of very few elements. Okay, so we look at iota and go like, we only got 4 elements here. This is known to be true, this is known to be true, this is known to be true, this is known to be true. Any one of these 4 can bind to psi, and any one of these 4 can bind to phi. Okay, so we'll just go ahead and say, okay, in this particular instance, I'm going to bind 1, okay, which is true to psi, and I am going to bind P or Q to phi. P or Q. Okay? One is a well-formed formula that is known to be true. That's why it's circled. P or Q is a well-formed formula. It is also known to be true because it is also circled, and in return, that is because it is in iota. And we don't question why certain things are in iota because that's given to you. So now we have satisfied that we found something for psi, we found something for phi, and then once the set of the patterns are satisfied, now we use the inference rule. Okay, we basically say inverse, and then we make a new well-formed formula. So because psi is actually 1, so now we have a new well-formed formula with 1 on one side, and then we have the ampersand, ampersand, and then on the other side we have P or Q. This is now a new well-formed formula, and it has to be in this space somewhere because this is the entire space of all the well-formed formula. So we find it, okay, 1 and P or Q. And now remember, it has already existed in this space from the beginning. The inference rule is only here to say, tag, you can now label this thing, you can now circle this thing, because now we know that particular thing is also true. So now we circle this, right? So is this illustrating, the relationship between, why we have the inference rules, what they actually do? All right, Elijah is typing something. And by the way, this is the first time I use this approach to explain propositional logic. It's not like I forgot how I explained it last time. It's just I like to find new things to do it. All right, so the Elijah's question is phi being assigned P or Q an assignment? Not so much an assignment. You can look at it as an assignment. It's just one way to say, okay, give me something for psi and give me something for phi. And since these rules have no specific requirement, we can just pick up anything. That's why. And then Jonathan said, so phi and the other Greek letter can comprise of anything in iota. Not only in iota, anything that is known to be true. So I can reapply the same rule, right? Okay? So observe this. I can now reapply this rule because this is the result of applying that rule once. But now I can reapply this rule, and I just go like, okay, give me something that is known to be true. Give me a well-formed formula that is known to be true. So this time I'm going to say, this time I'm going to pick not 0. Okay, and give me something that is also known to be true as our phi. Okay, and I can pick the same thing. There's no rule saying that I cannot pick the same thing because whatever I pick for each of the Greek letter only has to be a well-formed formula that is already known to be true. In other words, something that is already circled. There's no rule saying that I cannot pick something twice because the syntactic rule here does not say that they cannot be the same thing. So after I apply the inference, now we end up with not 0 and not 0 also has to be true. So now, in this space here, I find that particular well-formed formula because the well-formed formula is in this space already. It is just a matter of labeling whether it is known to be true or not at this point. So now we look up this thing here and go like, guess what? We can now label you and put a circle around you because now using the production, using the inference, we can now know that this particular well-formed formula is true. Okay, so let me go back to the text channel and read the text over there. How do we get the pattern? Is it given to us? Yes, it is given to you because those are the elements in zeta. That's that's the whole purpose of the set zeta, is to give us a whole bunch of these what we call inferences. And then the next question is, can you also infer psi or phi in this case? Um, yes. Yes, you can also have but that would be another rule. Okay, that's another rule for that. And then Jonathan says, but both are in set iota. I was wondering if you could use something not defined in iota. Absolutely. Okay, let's do that. So given the current state of this space and given what is already labeled, I would just pick not 0 and not 0 as my psi. And then for my phi, let me pick 1 and P or Q. Okay, so this is one application of the inference rule. Okay, so this is another application of the same inference rule. This is the third time we apply exactly the same inference rule, and this time, the thing that we're going to label is going to be not 0 and not 0, the whole thing, and 1 and P or Q. Now, this thing is in that space from the very beginning. We are just now labeling it and say that, we know this is true also. You're referring to not 0? Well, not 0 is from iota. Oh, disregard. Okay. But I think this exercise is already giving you guys an idea of what an inference rule is. It specifies a pattern to match, and then it specifies, okay, once we match this pattern, we can now, label something based on the pattern to also to be true. So let me give you guys, we only got 3 minutes left, but I'm going to give you a particular inference rule, which is not, well, let's see. It is applicable, but it has a certain pattern to it, because what we have here as this particular pattern, there's no actual restriction, right? Give me something and I'll make something new. That is not fun. Let me do something that is a little bit more fun. So this is going to be something a little bit more fun. I will say psi or, oh, this is not going to work. It's going to work in this case. It's not going to work in this case. However, it does illustrate something that has a particular requirement that is not easily met. Okay, so psi or phi is one thing, and then not phi or rho is the other thing. And then the production, okay, what we are quote unquote generating, or what we are labeling new, to put a circle around it, because we also know that is also true, is going to be psi or rho. Okay, so this time it is not so trivial anymore, because we are looking for a specific pattern. The specific pattern that we are looking for is, we are looking for something that is a disjunction. One component of the disjunction is phi. We are looking for another disjunction where one of the components of the disjunction is the negation of the same phi. So this phi and this phi, they have to be the same, although the psi here and the rho here can be whatever. So this is putting an additional restriction as to which two well-formed formulae that are known to be true can be utilized in this particular pattern in order to produce a new, well, I shouldn't say new, in order to label another well-formed formula to be true. And the new formula that is labeled to be true is kind of interesting because it kept psi, whatever psi is. Psi can be a huge, big, long, complex expression by itself. It also has rho, which can also be something that is huge, big, and complex, but it doesn't have phi anymore. Phi is not a part of the result. And by the way, if I were to use the term look ahead, this is really looking ahead because this is what we call resolution. Okay? And if you are, we got about 40 seconds left. So if you are thinking and go like, this looks absolutely awkward, okay? Are we really sure this stuff works? I mean, is this even valid? I will prove later on in the module that this actually makes sense, okay? The meaning of this in actual logic that we do is sound. And that's why this production rule, which is basically just syntactically matching something, is also making sense. Okay, this is resolution already, and someone may say, but since you earlier said that resolution only works when we have a CNF or conjunctive normal form, and all I can see here are the OR operators. How does that work? Well, when we get to CNF, we'll see better why it actually does work really well with CNF, with conjunctive normal form. So we are out of time for today's lecture. I am intending to stop here. I do recommend all of you to at least kind of try to understand these terms. You may not even need to rewatch the whole thing, but I do want to make sure that you guys understand that alpha is giving us all the basic symbols, constants, variables, and also these basically placeholders for well-formed formulae. So that's alpha. And then we have the next set, which is omega. Omega, in this case, is really easy. Okay, so omega to us would be and, or, not. Now, if you want to, we can also put implication in here. It is not 100% necessary, but we can stick it in there. Not a problem. Okay, because those are just the operators. And then we have zeta. Okay, so these things are in zeta. This thing here, okay, this thing here is one element of zeta. The other one, this one over here, is also an element of zeta. And then finally, we have iota. Iota is basically seeding the well-formed formulae space with things that are known to be true. But using the elements in zeta, we want to be able to propagate all these circles. We want to be able to circle more and more things. And the question is, can we keep circling things until we get to the one that we actually want to prove that it is true? Well, I shouldn't say it is true. It follows. Okay, if we want to claim that P and not R follows, okay, is implied by whatever is initially true in iota. The question is, can we use these productions? Can we use these inferences to get there? That really is the question that we are asking a system to solve when we are talking about propositional logic. And Jonathan is asking, is this type of abstraction used to make programming languages? Not quite. Okay, propositional logic has a very severe limitation in the sense that it cannot handle quantification. It cannot handle for all. It cannot handle there exist. So it has very limited application in reality, but it serves as the I hate to use the term, but it serves as the gateway to more complicated theorem proving techniques. So this is a gateway, mathematical system to more complex, mathematical systems for actually proving theorems. All right. Well, you guys have a good day too. This is where the fun begins. I can only see the B, but I'm assuming that's begin. All right, so for those of you who really want to think a little bit more and understand the context of all of this stuff here, look up automated theorem proving, and also try to understand why that is important now. I can talk a little bit more. You guys can sign off. For those of you who don't really want to know this because you don't need to. Okay, this is all additional stuff just to provide a little bit more context to what we are talking about here. Because the worst thing I can do is to give you guys a whole bunch of stuff and you say, well, we are trying to study this stuff only because it is part of tax class. I want to give you guys the context. Okay, I think that's important. So a long time ago, when I was a graduate student, and even before that, there were people trying to prove theorems already using computers, to basically use automated theorem proving. And back in those days, we don't have the processing power, we don't have the horsepower, and we also don't have the storage. There's just not enough infrastructure to do automated theorem proving. But there wasn't much application either. It was a novelty thing. Okay, people say, well, if we can do it, don't you think we can program a computer to do the same thing? So it was purely a research interest at the time, and go like, there's no really practical value at the time. But these days, it's a little bit different. Okay, so I'm going to show you a few things that is going to be relevant. One is called the hard bleed bug. It is, so you can look it up and read about it. Okay, but the bottom line is the hard bleed bug, which is a security hole, is here only because people were not careful when they wrote programs. And this one is at the heart of the SSL engine in open source products. So that makes it kind of really, really bad. But you can read about it. So the idea is, okay, is it possible for me to mathematically specify the proper outcome of a particular program, and then feed the system the actual program, and then have the system to say, can I prove that this program, the outcome of this program, is going to match what we want the program to do? That's the question. And as it turns out, that is a mathematical proof. Because if you can state the correct outcome after an algorithm runs as a mathematical expression that can either be true or false, and if you can use a theorem proving system so that it can look at the steps of a program and then step by step using the initial condition to derive the exit condition or the final condition of the algorithm, then you can match whether the final condition after running an algorithm is going to match what you expect the program to do. That is the reason why automated theorem proving is so important. Because if you just take the core, the most important part of an operating system, and then you specify on one side, you specify the proper outcome. On the other side, you have an automated theorem proving system. Then if the system can prove, if the automated theorem proving system can prove that this code does what it's supposed to do, you don't even have to throw test cases at the system, because now you have proven once and for all mathematically that this code is written correctly. That is the main driving force today why we are interested in automated theorem proving. So once again, propositional logic, what we are talking about here, is not going to be useful. Okay, it really is just the gateway to get into the more complex type of logic system that are actually needed for theorem proving. So I have no idea whether someone is still listening to me or not, or whether I'm just talking to my screen, but that's okay. I do that a lot anyway. So that's it. Okay, I'm just giving you the context of why this stuff can be important. Oh yeah. Well, eventually, we can put the QA engineers out of business. It's gonna be very, very difficult, because if we could do it already, we wouldn't have security vulnerabilities in software and operating systems and whatnot. So I think that day is not gonna come anytime soon. All right, so you guys have a good day. I'm gonna get into my office hour, so I will be online for another hour or so. If you guys have questions, go ahead and text chat with me. Otherwise, I'll see you guys next Monday, and that is exam one. So don't forget, exam one is next Monday. Whew, okay, time to get something to eat. Bye.